About ready to get started. Some more people are trickling in. Hopefully they'll be in by the time I'm finished with this short intro. So welcome everyone to the monthly seminar of the IAU Working Group on Active B-Stars. I'm Alex. I'm the current main seminar organizer, and it's my pleasure to welcome Dr. Sebastian Kamann from the Liverpool John Moores University. So Dr. Kamann did his degree at the University of Potsdam and then was very involved in the development of MUSE, which is an integral field spectrograph for the VLT, with which he looks at stellar clusters. Currently, Dr. Kamann is a UKRI Future Leaders Fellow and academic staff member at the Astrophysics Research Institute at Liverpool John Moores University. And today, he will be talking to us about, sorry, I had all my windows here, the fingerprint of stellar rotation on the color magnitude diagrams of young stellar clusters. Oh, and it was written on the screen, of course. So, Dr. Kamann, without further ado, please take it away.
Thank you very much, Alex, and thank you all for joining and for giving me the opportunity to talk to you here about some of the work that we've been doing on studying stellar rotation in young massive star clusters. And I thought I should start with some clarification of what I mean when I talk about massive star clusters. So when I talk about massive star clusters, I usually mean star clusters that can survive for a Hubble time, which then typically sets, say, a lower mass limit of the order of 10 to the 4 solar masses on these clusters. Now, when we look at the Milky Way, then we find that clusters of such masses are typically the old globular clusters with ages above 10 gigayears. However, this is not necessarily true when we look at other galaxies. And the best examples we probably already find in our nearest neighbor galaxies, namely the Magellanic Clouds, where we have young massive clusters with ages down to only a few mega years or even still forming. And I'm showing you here two examples that will be heavily featured throughout this talk. The first is NGC 1846 in the Large Magellanic Cloud, which has an age of about 1.5 gigayears and a mass of the order of 10 to the 5 solar masses. Similar massive is NGC 1850, which has a mass of only 100 million solar masses. Now, if we look at globular clusters, everything seems clear. If we create a color magnitude diagram, then at least if we look at it in optical colors, everything seems to nicely fit with the idea that we have a simple stellar population that we can easily describe by a single isochrone, as in this case for 47 Taq, one of the most well-known and most massive globular clusters in the Milky Way, which, as you can see here in the study from Del Olmo Dame et al., is nicely fit by an isochrone with an age of the order of 11.5 gigayears. However, when people then finally were able to look at these younger massive clusters in the Magellanic Clouds, they found a few surprises. And the first one that I want to talk about, we can see in NGC 1846. So this massive 1.5 gigayear-old, maybe young or intermediate age cluster in the Magellanic Cloud. Here you see its color magnitude diagram from a study by Mackey and Brody-Nielsen in 2007. And if you look at the main sequence turnoff of this cluster, then you already see maybe something strange. And to amplify this, let's compare this to some isochrones. And what these authors found was that the main sequence turnoff of this cluster appeared to be bimodal. And as you can see here, you can kind of get a nice description of this extended main sequence turnoff by assuming that the cluster is made up of two stellar populations with an age difference of about 300 million years. So people got very excited when they saw this, because this might show evidence for extended star formation in clusters. Or we might be looking at a merger of two clusters in this case, so a very special example of a cluster. However, astronomers continue to look at these massive star clusters in the Magellanic Clouds, and they found that such features were not restricted to individual clusters, but are really common. Like here you see a much younger cluster, NGC 1856 from a study by Milone et al. Apologies, the reference there is a bit cut off. Where again, we see that the cluster has an extended main sequence turnoff that we can nicely describe with 3 isochrones. And actually something similar has been found for all clusters younger than about 2 gigayears that were studied in this way with high resolution HST photometry. So this obviously rules out mergers because it doesn't seem right that every cluster is a merger. And also what people found when doing statistics over these clusters, like in this study from Niederhofer et al. 2015, is that the age spreads that were inferred from fitting isochrones to the data increased with cluster age. This also then, I think, basically rules out that these extended main sequence turnoff are caused by actual age spreads, because it doesn't make sense that the older a cluster, the more extended its star formation rate is. And this rather then calls for a stellar evolutionary effect causing these extended main sequence turnoffs. And it seems to be the case that what we're seeing here is really the impact of stellar rotation. So that stellar rotation is this evolutionary effect that causes these features. Why is this? Well, kind of in a simplified explanation, stellar rotation changes the hydrostatic equilibrium in a star. Because you have the pressure term supported by the centrifugal forces of the stellar rotation. So also the gravity changes, and then we have changes in effective temperature, surface gravity, which then basically causes the star to change its position in a color magnitude diagram. This effect was first described in a paper by Sebastian and de Mink in 2009, and is nowadays also included in stellar evolutionary models. Like for example, here you can see again NGC 1846. And in this case, again, the extended main sequence turnoff is fitted with different isochrones, but instead of changing the age as previously, now the initial stellar rotation of the star changes from no rotating stars to stars that are rotating very close to their kind of breakup velocity, where kind of centrifugal forces would start tearing them apart. And what you see here is that we seem to get an acceptable agreement between the data and the models also for rotating models without age spreads. With the apologies, something seems to be weird with my references here, but with the advent of the Gaia data, it was actually also then possible to confirm this link between stellar rotation, or V sin I, so the stellar rotation corrected for the inclination that we typically measure from spectroscopy, and the CMD position, not only for these distant Magellanic Cloud clusters, but also for lower mass clusters in the Milky Way. I'm showing you here one example that I was also involved in, led by Sebastian in 2018, about the low mass cluster NGC 2818 in the Milky Way, where you see that if you can finally clean it with the Gaia data for the contamination by field stars, you again see a nice, although quite sparsely populated extended main sequence turnoff. And you see here a clear correlation in the sense that the redder stars are also rotating faster, which is exactly as you would expect from if these color spreads were caused by stellar rotation. However, this wasn't the only surprise that was found when people studied these massive star clusters in the Magellanic Cloud. Another surprise was that the younger of these clusters seemed to show split main sequences. So let's look at NGC 1850, the other cluster that will be a main topic of this talk. Here in this study from Correnti et al., where they again looked at this cluster with Hubble Space Telescope photometry, you can see here that even after you clean for Magellanic Cloud field stars, which are the red dots, you already see that the main sequence down here seems to be split in two. And this becomes even clearer if we zoom in onto the main sequence. So we seem to have a red main sequence, which is more populated than a blue main sequence that you see here. Now there's also the third sequence here, which is caused by binary stars. So kind of the idea is that if you have two stars contributing to one observed star, then the star will be shifted to the red and will get brighter. So kind of what you see here, red wards of the main sequence are the binaries, but we can't really with binaries explain this blue main sequence. So again, there must be something that's causing this blue main sequence to occur in these clusters. And again, stellar rotation seems to provide the answer here. This has, for example, been measured for the first time in NGC 1818, a 40-million-year-old cluster that was studied by Marino et al. In 2018, where they got spectroscopy of stars on both main sequences. And they found that the stars on the blue main sequence all seem to show relatively low V sin I values, where the stars on the red main sequence were scattered to much higher V sin I values. So stellar rotation also seems to provide a natural explanation for these two main sequences that we observe in basically all of the clusters with ages younger than of the order of 500 mega years, approximately. And there's even more interesting stuff about these young clusters because they also tend to show rich populations of BE stars. So if we zoom into the extended main sequence turnoffs of these clusters, and especially if we look at them in H-alpha photometry, as done here in this study by Sebastian et al., again on NGC 1850, then we see that there's a lot of stars that show strong H-alpha excess. Now, I probably don't need to tell most of you what BE stars are, but I'm not an expert on BE stars, so I thought it would be good to include a brief introduction anyway. So when dealing with BE stars, we're dealing with fast rotating B stars that show decretion disks. And it is, there's some strong evidence that many of these BE stars are formed via mass transfer in binaries. For example, there's evidence for BE star X-ray binaries, like shown in this artist's impression here, where you have a B star orbiting a neutron star that's accreting some mass from the decretion disk of this BE star. It has also been found that BE stars are often in runaway systems, which then again provides evidence that probably the companion of the BE star had undergone a supernova explosion, which caused then the BE star to become a runaway. And there's quite a bit of literature about the link between BE stars and mass transfer in binaries. The question, though, is whether mass transfer is always required. For example, recently there was a paper by Kervala et al. Where they looked at one of the closest BE stars, Acherna, and their conclusion was that this system could have also formed without any mass transfer. So, and since these young massive clusters seem to provide us with rich populations of BE stars, and even more promising also, we know the ages of these stars. Maybe these young clusters can tell also enlighten us about what's behind these BE stars. So as a summary of this introduction, how does rotation impact young massive clusters? We look at the color magnitude of, for example, again, NGC 1850, then stellar rotation seems to impact the extended main sequence turnoff of the cluster. It also seems to cause the split main sequence of the cluster, and also then finally seems to cause these rich population of BE stars we observe in the cluster. But what are the open questions in terms of rotation and young star clusters? One is whether these populations that we observe, the slow and the fast rotating stars, are they actually discrete populations, or do we actually have a continuous transition from slow to fast rotators? Also, for these fast rotators, how do the typical rotation rates compare to the critical velocity? And then finally, what is the origin of these observed spin distributions that we have in the clusters? And then finally, maybe what makes a B star become a BE star? And these are the questions I want to try and answer in the remainder of this talk a bit, based on some MUSE data that we observed. So we used MUSE recently to observe a sample of young massive clusters in the Magellanic Clouds. And here you see our sample, which basically kind of tries to cover the parameter space from approximately 100 million years to an age of about 2 gigayears, which are the oldest clusters for which effect space linked to stellar rotation can probably still be observed. I want to focus here on the two clusters that I've mentioned now several times, NGC 1850 and NGC 1846. And let me start with the latter cluster to explain to you why we think MUSE is such a powerful instrument to observe these clusters. So if we take a single MUSE observation, as in this case, then it gives us simultaneous spectroscopy for thousands of stars. Thanks to its high throughput, we can also observe relatively faint stars of the order of magnitudes 20 to 22 in the visual. And the IFU nature of the instrument also allows us then to adopt techniques developed for imaging like PSF fitting in order to deblend the spectra of stars that overlap on the detector. Now, if we do this for this example, then these are, for example, the spectra that we get. And I highlighted here one blue star, a very faint one, and a red star, a very faint one. And if we look at their spectra, then, and in this case, the calcium triplet, we can immediately see that the effect of rotation here, in the sense that the redder star has a much broader calcium triplet lines, which correspond to a V sin I, in this case, of the order of 160 kilometers per second if you do the measurement. Whereas the blue star, we could only determine an upper limit of the order of 45 kilometers per second. If we do this for the entire sample, then we find the following. So here we again have the extended main sequence turnoff of the cluster color-coded by V sin I, and we see a clear trend between the V sin I and the CMD position as predicted by stellar rotation. But since the sample is so large, we can even go one step further and do proper statistics. And if we pick a small range in magnitude and then plot a plot the distribution of V sin I against the color in this small stripe here, then we see again the trend between rotation and color. And if we then create a histogram over the distribution in V sin I, then we see two clear peaks. So it seems to be that we really have two discrete populations, the slow rotators and the fast rotators. And in this case of a bimodal V sin I distribution, we have of the order of 55% fast rotators and 45% slow rotators. Thanks to the high throughput of MUSE, we can actually also go to relatively faint magnitudes. And what we then find, if we compare to the brighter bin, is that the fast rotators seem to disappear. So you see that in the slowest bin that we could study, there's much fewer fast rotators than in the highest magnitude bin. And this can also be explained because if we go down here in this magnitude range, where below a mass of the order of 10 to the 3, 1.3 to 1.4 solar masses, where the stars then have convective envelopes. And these are actually effective in breaking the stars because their magnetic fields coupled to the stellar winds. So, and this actually then agrees with the disappearance with the of the extended main sequence turnoff, and then also explains why we don't observe these features in, for example, the globular clusters. One nice thing that you can also do, since we are not only observing the main sequence stars, but can also look at the later evolutionary stages, and then we see that as the stars expand, all of the rotation goes away. And this you can also nicely see if you, for example, plot V sin I along the subgiant branch as a function of color. Then you see here how the stars, how as we evolve along the subgiant branch, the stars get break more and more. And then you can also compare this again to model calculations. And what you already see here is that we don't seem to have many stars that approach like critical rotation velocities, but that everything seems to be, say, of an order of 50% of the critical velocity or below, even when we leave the main sequence. All right, now I want to come to the cluster that's maybe a bit more relevant for this group, since it contains more massive stars and especially B stars, NGC 1850. And this has been one of the most complicated data sets I've ever dealt with, because I'm coming from cool stars, so I wasn't used to seeing spectroscopy of hot stars that have barely any emission lines. And to make things even more complicated, NGC 1850 is located right next to a very young cluster, NGC 1850b, that you see here to the very right of the images. And this is creating some strong nebula emission across the entire field of view. So the strongest lines that we have in our spectra, the hydrogen lines, are heavily contaminated by emission. And this made the analysis of this data set quite complicated. But I hope I can convince you in the following that we still got some exciting results out of these data nevertheless. So here are the stellar rotation measurements for this cluster. So we were able to measure V sin I for about 2,200 stars. And if you look at the color magnitude diagram here at the main sequence, and especially zoom in into the upper main sequence as you see here, then we see again a clear correlation between V sin I and color. And again, the faster rotating stars are clearly redder than the slowly rotating stars. And again, we tried to make narrow magnitude bins and see if we can find some evidence for a bimodal distribution. So here we again have V sin I as a function of color. And we see that for the brightest magnitude bin, there seems to be a more continuous transition. But then if we go down in magnitude, it becomes more and more obvious that at basically at the color where the two main sequences would be split, there's a jump in V sin I to higher values, which you can already see here, magnitudes between 17 and 18 in B. If you go even further down, you can again see this jump that seems to be happening if you move to redder colors. Obviously here, if we go down in magnitude towards B of 20 or so, things become a bit more messy because the signal to noise per star is typically lower. But here actually MUSE provides us with a very powerful tool, because we can then actually take all of the spectra that we have on the blue and red main sequences and just stack them, which then gives us basically one combined spectrum with a more or less infinite signal to noise. And we also get kind of an automatic correction for the statistical correction for the inclination. And if we do this stacking exercise as here, then you see that we finally are also able to not only observe the strong hydrogen line, but also get to some very faint helium and, for example, silicon lines. And you see here that for the red main sequence stars, these lines are significantly broader than for the blue main sequence stars. And if we convert these into statistically corrected rotation velocities, then we find for the blue main sequence stars an average rotation velocity of the order of 127 kilometers per second, and for the red of the order of 233 kilometers per second. These values are actually quite well comparable to what has been found in the field. So this is an early study by Royer et al. In 2007, where they found for example, late type B stars, which are similar to those, or early type A stars, which are similar to those that we see on the split main sequence, also bimodal distributions. And especially the fast rotating stars have peak around 200 to 250 kilometers per second, in quite good agreement with our measurements. For the slow rotating stars, they seem to be finding smaller values. If you remember, ours was at around 100. So there might be some discrepancy here. However, I think one interesting bit of information is that the critical velocity for such stars, as in our samples, is of the order of 450 kilometers per second. So even for the red main sequence, where the fast rotators are, the stars only seem to be spinning of the order of 60% critical. And this is actually in quite nice agreement with some recent model comparisons done by Chen Wang et al., where they found that the split of the two main sequences, so the split in color, can already be explained if you just assume moderate rotation, and that rotation really close to the critical value isn't required. They looked at another cluster with a similar age than NGC 1850, NGC 2864. And what you see here is the color difference compared to non-rotating stars that you expect for different rotation rates relative to the critical rotation velocity. And the observed color differences are here, and they correspond to something like 50% critical. So their conclusion also was that rotation rates of the order of 0 to 35% for the blue main sequence and 50 to 65% for the red main sequence can explain the observed color split, which I think nicely agrees with our observations. Although I want to raise a small caveat here that some model predictions still seem to be differing between the models. And for example, in the models that we compared to our data in NGC 1850, which were cyclists, whereas I think Chen and her group used MESA models. For example, what we observed in these cyclist models is that what we predict for stars in NGC 1850 is that their rotation rate first drops quite steeply and then stays constant across their entire main sequence lives. And these drop, I think you don't observe in the MESA models, for example. But it's interesting to see that the rotation rate of a star, of a B-type star, barely seems to change over its main sequence lifetime, according to the models. Because what seems to change is the critical velocity of a star. So as the star approaches the end of its main sequence lifetime, which is of the order of 350 million years, you see that the critical velocity drops down as the internal structure of the star changes. And if you take the ratio of the two, then you would kind of find automatically that the function of main sequence lifetime, the ratio between the actual rotation velocity and the critical rotation velocity increases. And that even if at the age of NGC 1850 of 100 million years, the star isn't rotating critically, it might be doing so at the end of its main sequence lifetime. So something very similar has been done in a study by Ben Hastings et al. And this is basically what these plots are also based on for NGC 1850. But it's interesting that we observe this, because if we then look again at the BE stars, they also seem to be clustered around the main sequence turn. So we were able to also study the BE stars in the MUSE data. So what you see here is a color magnitude diagram where the color includes the H-alpha narrowband filter, and the stars in the MUSE data are color-coded by the equivalent widths in H-alpha. And the blue stars are the H-alpha emitters, so those you would expect to be BE stars, and they also all have H-alpha axis in the photometry. And if you create the relation between the H-alpha equivalent widths in the MUSE data and this color, then you see a nice linear correlation, which I was quite happy with, because it told me that despite this strong nebula emission, we still seem to be able to get some useful H-alpha measurements for our spectra. But what's really interesting is that the BE star fraction strongly increases to the turnoff. So going from only of the order of 10% at the lowest mass bin to something like 50% at the highest mass bin. This is something that has also been found, for example, in a study by Milone et al. Based on HST photometry. But then you ask yourself, could this be caused by the lowering of the critical velocity? So that basically as the star approaches the main sequence turnoff, it becomes a BE star. And could this then be the single star pathway to a BE star? Well, I think it's too early to say this, also because if you assume you can, under certain circumstances, also achieve a similar effect using only binary systems. But I think it's still something that deserves further analysis. And I think there's a huge prospect for the future work with MUSE, because if we go back to the theory predictions, then we basically currently only have one measurement at 100 million years. But basically the other clusters in the sample, like NGC 1866, which is 200 million years old, and NGC 1856, which is 300 million years old, then kind of allow us to probe these model predictions at different times of the evolution of the stars. And then we can really check whether the rotation velocity of these stars, for example, stays as constant as predicted by the models. So this is something that I'm really looking forward to doing in the coming months. But what's also interesting, when we look back at the BE stars here, is that there seem to be two types of BE stars. So we have a main population on the main sequence, and then we have another quite rich population that's red dwarfs of the main sequence. And this can be explained by an inclination effect, in the sense that these redder stars are observed equator on. So we're looking at the star through its disk. And then we get some extinctions by the disk, and then we have this so-called shell stars phenomenon. And we also see this quite clearly if we compare the spectra of normal and strange BE stars, or shell stars, because the shell stars show quite a lot of absorption lines caused by, for example, iron 2 or silicon 2 that are caused by absorption in the disk, and that we don't observe in the standard BE stars. And furthermore, the shell stars also have double-peaked H-alpha lines, as you would expect if there is a disk that you're observing the stars through. The nice thing is, since the sample is relatively large, so we have of the order of 220 spectroscopically confirmed BE stars, we can use the number ratio of shell to BE stars to estimate the disk half opening angle of the decretion disks. And the value we get of 14 degrees is a nice agreement with an early study by Hanushik et al. Only Hanushik in 1996. So So we can also learn with the MUSE data something about the disks surrounding these stars. And then finally, we can also look at the rotation rates of the BE stars and the shell stars. So here's cumulative distributions of the V sin I measurements. Apologies there for some reason. The units here don't show up. So on the x-axis, it's V sin I in kilometers per second. But what we see is that, as expected, the BE stars seem to be faster rotating than the normal main sequence turn-off stars. And again, the shell stars, which are BE stars observed more or less equator on, are again faster. But also what we observe is that for the BE and shell stars, our distributions don't extend to higher values than for the normal stars. So, and I think this is also in agreement with other studies, for example, by Dafton et al. For the Tarantula Nebula region, where they found similar, where they observed a similar trend. So, and then you ask yourself whether there's additional requirements that give rise to the BE phenomenon, because it doesn't seem to be the case that in general BE stars are just rotating faster than normal B stars. One caveat here that we need to take into account is equatorial darkening, namely that the fastest rotating portions of the star are also the faintest, so they're most difficult to observe. All right, so what have we learned from the observation of the stellar rotation in young star clusters? So indeed, there seems to be evidence for two populations of stars. So we have slow rotators, which seem to be rotating with of the order of 20 to 30% of the critical velocity. And then the fast rotators have 50 to 60% of the critical velocity and seem to make up the majority of the star in each clusters. And especially for the fast rotators, we find similar rotation rates for field stars of the same spectral types. But then still the large fraction of BE stars suggests maybe still the presence of near critical rotators near the turnoff of the clusters. And that then leaves us with the question, okay, but then what causes the distinction into slow and fast rotators in clusters? And this is what I want to spend the rest of my talk with, going a bit into the different scenarios that have been proposed to explain this. And the first idea was that maybe binaries play a role, because it has been observed in the field, for example, by Abd and Bonyarak in 2004, that tight binaries with periods of the order of 500 days or less are typically slow rotators. So here you see the mean V sin I of A dwarfs as a function of in binaries as a function of the orbital period. And you see a clear drop in V sin I as you approach shorter periods. And then at some point you have tidally locked rotation, or sorry, synchronized rotation. And this is explained because the binary members then are braked via tidal forces in the clusters. And if you translate this idea to clusters, then you could think of a scenario where all stars are born fast rotators, and then the binaries cause the slow rotators. Now, with the MUSE data, we were able to put some constraints on the binary fraction of the two main sequences, because the data for the two clusters was observed over of the order of 15 epochs. So we could detect binaries via radial velocity variations. And in both of the clusters that we observed, we found similar binary fractions for the slow and the fast rotators. Whereas if all these blue main sequence stars would be in tight binary systems, then I would have expected a strong axis of binary systems along this blue main sequence. An alternative that's also to some extent linked to binaries has been proposed by Wang et al. 2022, where they based their model on two observations. The first was that the blue main sequence stars seem to have bluer colors than predicted by even non-rotating models. And they also seem to have a different mass function, or a top-heavy mass function compared to the red main sequence stars. And the idea that they come up with in order to explain this is that at the early cluster evolution, you have orbital decay of very tight binaries. So you have very tight binary stars that decay and merge, and this merger will then lead to rejuvenation of the star. And the merger product might also then afterwards, after it resettles, become a slow rotating star. One prediction of this is that almost no blue star should be in a binary system, which again doesn't really seem to be what we're finding in the data. But with this scenario, I'm less confident, since there seem to be some weird selection effects into play, because then the binary stars could also migrate from one main sequence, from the blue main sequence to the red main sequence. So there's certainly more work to be done also on this scenario. One scenario that Nate Bastian and I have worked on a bit is based on another idea. And especially it's based on the idea that if we look at younger masses, so stars of 1 solar mass or below, then we find that their period distributions in many young clusters in the Milky Way also seem to be bimodal. For example, if you look at H Persei with an age of 13 million years, you see a clearly bimodal distribution of the spin periods. And then what you also observe is that if you increase in cluster age, then the low period fast spinning stars seem to disappear, which again can be explained by this breaking of the star by its magnetic field coupling to the stellar wind. The interesting bit is if we translate this idea to higher mass stars, where this breaking disappears, then we find, as shown here from a paper that Nate has led in 2020, that if we set up a cluster with stars of masses of 1.5 to 1.7 solar masses with a fixed surface velocity, then it will basically retain that velocity for that spin velocity for its entire main sequence lifetime, more or less. So yeah, so basically, if we find a way to set up the stars with some bimodal spin distribution during their pre-main sequence lifetimes, they will keep that bimodal spin distribution through their entire main sequence life. But what could be this what could be the mechanism that establishes a bimodal distribution during cluster formation? One idea that we had was that maybe it's disk locking, so that the spin of a star depends on how long it can hold on to its pre-main sequence circumstellar disk. Because when the star is still surrounded by the disk, you can have magnetic interaction again between the star and its disk, which would then remove angular momentum. And what you see here is that depending on the disk life that you assume, you can set up stars with very different surface rotation velocities once they settle onto the main sequence. Again, this is for 1.5 solar masses, when you see that a star that loses its disk early on speeds up to become a fast rotator, whereas a star that holds onto its disk for much longer becomes a relatively slow rotator. Now, this is of course based on relatively low mass stars, and the extrapolation to more massive stars is still unclear. So there's definitely still a bit more work to do, but I still think this could be an intriguing scenario to explain the observed spin distributions in young star clusters. So yeah, just to summarize, in this scenario, the spin velocity would be set by the disk lifetime, in the sense that a star that loses its disk early on would be a fast rotator, whereas a star that maintains its disk would be a slow rotator. But what could remove the disks of the stars? Well, the disk lifetimes depend on the environment, and you can have photoevaporation by hot stars, for example. In this study by Andrew Winter, you see that as they have the disk lifetimes on the y-axis, and as a function of the UV radiation field, the stronger it gets, the lower the disk lifetimes. So yeah, photoevaporation, so that the presence of hot O stars nearby could remove the disks. In clusters, dynamical encounters with other stars could remove the disks, or we could again have binary stars removing the disks. The predictions from this scenario would be that we have more fast rotators in denser environments, and the fast rotators should also be kind of centrally concentrated inside the clusters. All right, this brings me to my summary. So yeah, I wanted to illustrate to you how we really think that young and intermediate age star clusters host distinct populations of slow and fast rotating stars. And these rotation velocities aren't that extreme after all, but they are actually quite similar to those observed in the field. But what causes them is still a matter of debate. And especially the question is, do binaries play a role, or maybe do disks play a role? And if you want to learn more about binaries and star clusters, because I hope I convince you through this talk that they're quite important, then maybe you want to save a date in September, where we're organizing at the ESO campus in Garching a conference on the interplay between binaries and star clusters, where we hope to discuss topics like those that I've presented to you in much more detail. And with that, I'd like to thank you for your attention, and I'm happy to take any questions.
All right, thank you very much, Sebastian. I'll clap on behalf of everyone. This is a really, really nice talk. So there are already a few questions in the chat. So first one by Myron Smith. Myron, I don't know if you would like to ask it yourself or...
Hello, Alexandra. Can you hear me?
Yes.
Yes, quite early here in the morning in Arizona. No, you can go ahead and read my question. He may have already partially answered it.
Okay, great. So the question goes as follows. You mentioned in your talk as a caveat that there are discrepancies between observed CMD positions and stellar evolution with rotation included. Can you elaborate on this caveat?
Sorry, can you repeat the question?
Yes, of course. So you mentioned in your talk as a caveat that there are discrepancies between observed CMD positions and stellar evolution with rotation included.
Yes.
So can you elaborate on that?
Yes. So was this referring to this? So I mean here, yeah. So let's maybe explain this based on Chen's paper here. So what you have here, so you see the two main sequences as solid blue and orange lines here. And what you find is that while the red isochrone describes nicely the observed position of the stars, of the red stars in the CMD, the stars on the blue main sequence seem to show bluer colors than even the isochrone without any stellar rotation, with very little stellar rotation. So there seems to be some discrepancy between the colors or the effective temperatures predicted by stellar evolutionary models and those observed in the CMDs. So, and the idea that one idea then that could remove this discrepancy is that, okay, these stars just appear younger than the cluster age. So they've been rejuvenated by some process. And the idea that has been put forward in this paper was that, okay, it's this, if you have some way to merge stars, then you can compensate for this discrepancy. Was this what?
Yes, thank you. I guessed later after I phrased my question that this is what you were referring to. Thank you.
All right.
Okay, we also have another question in the chat from Gregor Rao, which is, wouldn't you expect a continuous distribution in rotational velocity rather than a bimodal distribution in the disk locking scenario?
Yes, that's a very good point. So indeed, we would, there's no like, intriguing argument why you always expect a bimodal distribution from this. So what we found when we calculated these models is that depending on when you lose your disk, a lot of stars were approaching relatively high V sin I values, very close to the critical ones early on. So actually quite a few models ended up very close to V sin I. So then based on this, one could argue that, okay, if we lose the disks early on, then we get quite close to some critical value where then other effects kick in. But yeah, I'd also like to see this being modeled in a bit more detail. So I'm an observer by training, so this is kind of as far into the models as I feel comfortable with. But yeah, it's a very valid point.
Thank you. We have another question in the chat and then a hand that's been raised. So I'll go with the question in the chat quickly. Connie says, thanks for a nice talk. You made comparisons between model predictions for V-crit and measured V sin I. I would be curious to know how your data and models compare with internal near-core rotation rates, which we now have from astroseismology for a sample of about 70 stars with masses ranging from 1.329 solar masses. These are field stars, though, so roughly solar metallicity.
Yeah, I have to admit I haven't looked at this comparison yet. So, yeah. I mean, with astroseismology, you can obviously get a much more detailed idea of the interior of the star, that what we can do here. So yeah, I'm afraid I cannot give a really convincing answer to this. Yeah, I would need to look into this. Apologies. Yeah. This is something, yeah, that I haven't checked so far.
Okay, and I guess Kami says that she can help. So now
yeah, I'd be really curious to learn more about this. So yeah, this is.
So we have a few raised hands. I think the first one is Anahi. Oh, I'm sorry, you're muted, Anahi.
Sorry, I thought I wasn't muted. Thank you very much. It was very interesting to hear you. And I have a little comment and also a question. You showed a plot from taking data from cyclists, where you could see this decrease in the rotational velocity at the beginning of the main sequence in evolutionary models. And you commented, you mentioned that it was different from what we observe in other from other models. And of course, it's true, this little feature, this decrease in the rotational velocity is due to the fact that those models start with solid rotation, and then you have a readjustment in the internal structure decrease, and then you set in that minimum there, which in my opinion, it is the good initial rotational velocity that should be considered. And because it's related to the fact that the star got this structure, of course, in the single stellar evolutionary model. There. And in fact, we tried different structures at that point, and then you observe that whatever you put the star, of course, taking into account the physics of those models, everything would settle in that minimum, which is what you, I think that you observe in MESA and other codes. So, but then my question, this is my first question, is perhaps when you have a merger or something like of the kind, or something that changes the structure of the star, would you settle in some kind of minimum that could then be considered the evolution of a star? That was like an idea, but that was not my question. In fact. That was a small comment. So the question, this was to clarify this point, because I knew about how those were computed. No. I could mention. Sorry. So the
thank you very much.
You have these clusters, and there's so many data, positions, velocities now with Gaia. Do you observe any differences in the distribution in the position of the star cluster of these populations, or different populations of stars you observe with large Vsin of I, small value, or it's just the same distribution in the cluster field or the angular proper motion of the stars? My question is, perhaps these stars belong to different dynamical or position location in the clusters. That was my question.
Yes, excellent point. Yeah, so I think we still don't have a conclusive picture on this. So at some point I also tried looking at the kinematics of the fast and slow rotating stars, like whether they have different velocity dispersions, or whether one population is rotating faster than the other. So rotation in terms of cluster rotation, not stellar rotation, but didn't see anything obvious. And I'm not aware of any real kinematic differences between the populations. What has been observed based on HST photometry for some clusters are differences in the concentration of the two populations. But there it seems to be a bit of a mixed bag, in the sense that you can't always say that the fast rotators are more centrally concentrated than the slow rotators, or the other way around. But it seems to be that for some clusters the fast rotators are more centrally concentrated. But I think we need to enlarge our samples as well. So yeah.
Okay, thank you very much.
Thank you.
Okay, so we have time for a couple more questions. So there's two hands up. First, Dietrich.
Yeah, thank you. Sebastian, that was a wonderful talk. Thanks a lot.
Oh, thank you, Dietrich.
You mentioned the possibility that there may be an indication of single star evolution of BE stars. Now, when we look at the confirmed binaries with a BE star, then we have two classes. One are BE stars plus a neutron star, and the other class are BE stars plus a subdwarf star, hot subdwarf. And test observations suggest that these two classes, if you will, of BE stars are very similar. This is not astrosseismology, but it suggests that these stars are really similar. And if the formation of the neutron star and the formation of the SDO or SDB star takes place early, then of course the BE stars would probably evolve more closely to a single star track than a binary star track. And so such evidence could be spurious, couldn't it? Or misleading?
Yes. So I mean, there's, I think, yeah, I wouldn't bet my house on that. What we observe is really evidence for single stellar evolution to BE stars. I think it would be really informative to look at these older clusters and then see how these stars evolve as they approach the main sequence. I just, to me, it was striking that the fraction of BE stars is just so high in this, towards the extended main sequence turn of NGC 1850. So I was wondering whether we can explain fractions of the order of 50% from these mass transfer binaries. So
the fraction is going up. The mystery, at least the mystery to me, is that there are no white dwarf companions. There may be a few in the Magellanic Clouds, but they are still probably waiting for a confirmation.
Yep.
Anyway, thanks very much, Sebastian.
Thank you.
Okay, and we're just rounding out on the hour, so I think we have a question for one last quick. We have time for one last quick question from Norbert.
Yeah, Sebastian, thanks very much for this beautiful talk. It was a nice summary of the status of the field. Really appreciate it. I have a question to you as an observer. So it's great to see what you can all do with MUSE spectroscopy. It's really a new universe you're opening here, so it's really great. What I'm wondering is, if you look at the color magnitude diagram which you just show here, then we would expect that the reddest stars in the thick main sequence band there would all be mass ratio 1 binaries. Yeah, because you briefly explained that if we have binary stars, then they are redder and brighter, and that's why they end up on the red side. Well, I'm wondering whether you've tested that through your spectra, whether you can actually see that.
Yeah, So we tried looking into this, and so far the results are not entirely as we would expect. So we kind of expect to miss out on these 1-to-1 mass ratio binaries, because then we just run into the problem that if one star moves away from us, the other moves towards us. So the line shifts cancel out. But there should be a sweet spot with mass ratios of the order of 0.5 to 0.6, where we should see most of the binaries. But this doesn't seem to be the case. But then we actually started looking into this a bit with Julia and Chen, where Chen provided some of her models, and then we tried combining them with our with our observational biases and then see where in the CMD should we detect most of the binaries. But it's still in the early stages. But yes, you're totally right that we expect an overdensity of binaries somewhere.
Okay, thanks very much. I look forward to how this continues.
Yeah, thank you.
Okay, so just let me thank again Dr. Sebastian Kamann for a really nice talk. Thanks to everyone for connecting. Please stay posted. We will have another seminar next month, and all the details will be sent out to the community shortly. So yeah, Sebastian, thanks a lot, and have a good rest of your day or end of your day, wherever you all are. Until next time.
Thanks very much for having me. That was great.